All right, welcome back, everybody. Today we'll talk about how, one, I was able to get the in situ type installed, so now we'll be able to phenotype our cells. And then we'll also start to look at normalizing our data. So we'll normalize our data with SCTransform, which is a Seurat function. So SCTransform. You can see I've clicked on it. They had a publication a few years ago, this guy here, 2019, but it's a little bit better than just log transformation. We'll talk a little bit about that. But first, to start off, how did I get in situ type installed? Well, it was kind of a pain in the butt. What I had to do in the end was reinstall the R version that I have. So here you can see I have 4.1.2. This also has some issues with Seurat, and I'm not 100% sure why. We'll talk about that later as well. And then what I did is I deleted the rlang folder in the R environment. You go library, R4.1, blah, 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 blah. And then down here, they have the renv, R environment, or not the R environment, I'm sorry, rlang. I deleted this folder and then reinstalled with the dependencies as true, and then voila, the in situ type was able to be installed, which is interesting and frustrating at the same time. But let's go ahead and start with creating a new script. Too much stuff happening. All right. So I think that's the shortcut. We'll do our libraries first. Libraries. So as usual, we need to do library Seurat lowercase l. Great. And then library, and then tidyverse. This will come in handy with some of the piping stuff in the second script, but we'll keep it here just for the sake. And then we'll go ahead and create another one. So Command Shift or Control Shift R, and then we'll load in our data. Load in data. So here we'll load in the Seurat object that we had downloaded. It has our transcripts. Let me see. I hope I didn't delete the wrong one. Yeah, looks like we're good. Cool. All right, sorry. So we'll do object, we're just gonna call it object equals, and then read RDS, and we wanna go into our data folder, and then the only thing that's in there. So this is gonna take a little bit. I'll come back when this is all said and loaded. All right. So now we can see that our object is loading in. It's super large. And so what I think we should do with our object is see what we can pull out of it that we don't really need for the current steps of our analysis, right? So a 14 gigabyte object is fairly large. And the first thing that came to mind from last time is actually this transcript coordinates slot here. So this miscellaneous, we can see that it's a list, so we'd have to pass in an empty list if we want to replace it. But let's just go ahead and look at how big that slot is. So we'll do explore size, for example. We can do print, and then we can use object.size in order to put this into something that we can understand. And if we do object @ symbol, since it's an S4 object, miscellaneous, yeah, we can keep going. We'll look at, there's only one thing in here, so it doesn't really matter, but the transcript coordinates, and then we can pass in units to this print as megabytes. And if we go ahead and run that, we'll see the size in megabytes that just the transcript coordinate slot is of our Seurat object. And we'll see that this is rather large. Yeah, so 8 gigabytes just for the transcript coordinates in our Seurat object. So let's go ahead and pull those out. So we'll do extract and save transcript coordinates. Okay, so transcripts, we'll just call it that. Transcripts equals object at miscellaneous $transcript coordinates. So if we go ahead and run that, it's going to take a little bit because it's very large. Hopefully it goes. There we go. So it looks like it's a data frame. We can do, to make sure, class transcripts. Then we'll know what to use to save the object. Yeah, it's a data frame. Perfect. And then what I want to do is use data table. So let's make sure that we have data table installed. Library, data, there you go. Perfect. On Windows, have so many things that are interesting. First thing is we can use multi-thread in order to save and read in data, which is fantastic. It saves a lot of time. So let's go ahead and save our transcripts for use later. Okay, so the function within data table to do this is fwrite. There we go. And then we can see here x is the object that we want to save. So we'll save transcripts, and then where do we want to save this? Let's do it in data, and then we'll call it transcript locations.csv, and then we can do .gz to save some space. And this should be fairly quick if I remember correctly. There it goes. 10 seconds or so to save the file. And then once this is done, perfect. We can go ahead and clean environment. We'll do this a few times. That way, trying to talk and write at the same time. That way we don't end up with too big of an environment here. We can already see that it's at 21 gigabytes, and that's not something that I'm very comfortable with. I do have enough, but for the sake of everybody else, it's not ideal. So what we'll remove is transcripts. Great. And then we'll run GC. So this is garbage collection, and if we do full equals true, it'll remove all of the objects that are still in the background. So right now we can see that even though we remove transcripts, we still have 21 gigabytes being used. So if we do this full equals true, hopefully that brings it down. There we go, down to our 14, closer to our 14 gigabytes. But now that we have our transcript saved, there's no use in keeping this object slot occupied by that transcript information, right? So we can remove transcript info, we'll do that, from object. And to do that, we can do this, and we have to go and check the object type. So our object is S4, I should say, our slot type. And then the slot that we want to overwrite is our miscellaneous slot, and it's a list. So what that means is that we have to pass in a list here. So we can do list and then just put null or an empty list in there. Awesome. Now we have our Seurat object that is 5.4 gigabytes. So we're getting something down that's a little bit more manageable. And again, we can do GC full equals true. And this will clean out everything in the background. Hopefully, perhaps it's locked into the object. It should work. If it doesn't work, then we'll do something else. It doesn't look like it's working, but we can go ahead and do save RDS. Now we have a object that's no longer with our transcripts. So let's save this object, and we can always come back to it later. It has all of our assays. It just doesn't have our transcript locations, which is fine. We might want that later. So we'll call this the human frontal cortex no transcripts in our data folder. So go ahead and save this. It's going to take a little bit of time. It is 5 gigabytes, and the save RDS compresses. So when it's all said and done, I'll come back and we'll continue from there. All right. Now we have our object saved. I don't know why the file size is still as large as it is. So what I'm going to do is we're going to reset the environment. We can do this by doing rm list equals ls. So this is just going to remove everything that we have in our global environment. Poof. Then we can do gc full equals true, and that should hopefully remove everything that we have in our environment. Restart our session, restart R, and since there was nothing in our session, hopefully it's quick. Alternatively, we could do this. We're just not going to save it. Poof. And then we'll go back to our Cosmics folder and we'll just open up the R project again. Yay, so much faster. Oh no, we lost our script. That's fine. I have it copied to there. Yay. Okay. Now what we can do is we can read in our no transcript object. So object is going to equal read RDS, and then we can go back to that data, human frontal cortex, no transcript. And then this should read in hopefully rather quick. There's a couple other things that I think we can remove from the Seurat object as it is right now. And that'll be our reductions. So the next thing that we're going to do is after this, we'll normalize our data, and then we'll go through some of those dimension reductions, specifically principal component analysis, and then UMAP following that. So now that we have our object read in, let's look at the assays. Assays in object. Cool. Assays and then object. So this is going to be the kind of the experiments that they have in the Seurat object. And there we go. So we have false code, RNA, RNA normalized, and then neg probes. So from the Cosmics SMI website, so if we load this back up, we can see that they have false negatives or false positives in two different ways. They have a negative, which is the negative probes, and then they have these false codes. So there's just two different ways that they're measuring false positives in their data, and we want both of those to be very low, right? Because that means that our data is not noisy, or there's not false positives showing up where there shouldn't be anything. But we can remove the RNA normalized because that just, we'll normalize our data the way that we want to. So in order to do that, what we can do is do object at assay. So we'll use the S4 assay slot, and then RNA normalized, and then we can set this to null. Perfect. So we can see that our object shrank a ton here as well. So if we go ahead and do GC full, GC garbage collection, full equals true, we'll see if we can shrink that down a little bit more. There you go. Great. Now, as I mentioned before, we can look at what reductions they have performed. What reductions are in object. So these are the dimension reductions. In order to do that, we can use reductions the same way that we used assays. So reductions, and then pass in our object, and now our object does not have that RNA normalized. We can see that we have approximate UMAP and then PCAs. And then since we're going to normalize our data the way that we want, we can go ahead and then run our PCA and our UMAP the way that we want to as well. So let's go ahead and look at this object slot. reductions, we can see that this is a list as well. So in order to replace this, it's basically the exact same way that we did our transcripts. We can do objects reductions equals list. Remember, it's a slot that has that's made up of lists, a list, and then we can pass in null. It's just going to be an empty list. Poof. You can see our size didn't shrink that much, but that's okay. And now we want to save our fresh object. So we'll do save RDS, so we'll compress it, object, which is a fresh object, and then data, human frontal cortex, fresh.rds. So then this is going to be the object that we'll be able to go, it'd be helpful if I put it into quotes, eh? This is the object that will then read in, and we'll be able to run our own normalization, and then we'll be able to run PCA, UMAP. We can look at those, and then we can also do things like clustering. So we'll be able to see which clusters of cells are being assigned to the same ID. So when this is done saving, I'll come back and we'll continue. All right, it looks like our object has been saved. So let's go ahead and make a new script. What we can do is set up our library. So Control Shift libraries. We want our Seurat library. Great. We'll use our tidyverse library. And we should actually be good with those too. So we'll run those, make sure they're loaded and happy. And there we go, got our Seurat running again. And tidyverse, because we restarted R. Now we can read back in our object, or we can keep using this one. But if we're going to run the script separately, we'll do object read RDS, and then data, human frontal cortex, fresh. Perfect. That's just going to be the same thing that we have here. So I had previously mentioned the negative probes and the false code IDs. So if we go and look at this object, we can see our assays. We have 3 here, but we want to make sure that in our RNA assay here, we don't have our negative probes and we don't have our false codes. When we're normalizing our data, we want to normalize just the genes that are associated or that would describe those cells, right? Because with that normalized data, then we'll be able to go through and identify which cell they are. We'll be able to cluster them better. If the false positive probes, negative probes, and the false codes are in the data, they're not truly biologically part of the cells, right? So if there's more false codes, that's not going to help us identify, I don't know, whatever brain cells that are there. I forget exactly which cell types they were, but we want to keep the RNA just RNA. In order to do that, it's actually really easy. So let's check false codes and negative probes, PRB, in RNA experiment, RNA assay. All right. This is really easy to do. We can extract out the RNA assay genes or the targets by cells using get assay. So we can do counts. Yeah, counts equals get assay and then data. So if we want to look at the actual gene expression or the target versus cells, we'll use data of our object. So object equals object. And we just slide it in the first one. And then assay equals RNA. So we want to check in our RNA slot because that's going to be the one that we're going to normalize. You can run this guy. There we go. Pretty quick. So then let's check our negative probes first. Neg PRB first. So to do this, we can let's look at the dimensions of counts. So this will tell us which way our genes should be in. Okay, so we have 6,278 rows and 188,000 columns. So our columns are going to be our cells and our rows are our genes. Let's go ahead and we can just check this out here. Head counts, we'll do row names. Row names counts. Yeah, there we go. So we can see our genes there. And what we want to do, row names of our counts, we want to see whether or not it has the NEG PRB. So if we go up here, it should be pretty easy to look at the dimension names. We can see here, NEG PRB is the name of their probes. So if we go back here, we can look at grep. So we can grep NEG PRB, just as these IDs are here, capital N, capital P. And we want to look at what is piped in, right? So row names, if we just put a dot here, that'll tell grep, okay, we're passing in the data and it's going to go there. And then we want to look at the actual values. So value equals true. So for example, let's run an example down here. Say we wanted to look at CD3. If we do this, we'll do the row names, we'll pass the row names, which are going to be all of the gene names, into grep. We're going to look for CD3 in our row names, and we were going to pass out any that has CD3 as a part of it. And here we go. You can see that there's actually a handful in here. And then the one that usually is associated with the CD3 protein is CD3. So this is going to tell us which cells are T cells or lymphocytes. I'm talking too much. All right, so we're going to look for the negative probe in the same way that we did our CD3. So if we go ahead and run this, okay, so it doesn't look like any of our negative probes are in our RNA experiment, which is good. Now let's look for our false codes. False codes. Let's go up here to false codes. We'll look at our data and then dimension names. So we can see that this is false code, capital F, capital C. So we can copy this, paste, and then look at false code. And then it's going to look for false code in any of the names of our RNA assay. And it looks like none over there, or none are there either, which is good. So this means that the RNA assay that we have only has genes in it for the targets. So that makes our lives a lot easier moving forward. So, as I previously mentioned, we have this Seurat function that's called SCTransform. It's actually capital S, capital C, capital T, just like this. So we're going to transform our data just like this. And what is nice about SCTransform is that in their paper, they say that the SCTransform holds on to biological information a little bit better than just regular log transformation does. So if you're using SCTransform, it's going to handle the variation that comes from just technical error. It's going to handle technical error better and make sure that your biological information is being maintained, which is what we want. We don't want our technical issues weighing in more than the biological part. So in order to do that, we will now transform with SCTransform. And we'll just keep it super easy. what we'll do is we'll specify our new object. We want to keep our SCTransform output in SCTransform. We'll pass in our object. The assay that we're going to transform is going to be our RNA assay. So we have to tell it that. It doesn't know that right off the bat. We'll do assay equals and then RNA. And then what would we like our new slot in assay to be called that has our transform data? And what I'll do is just call this new assay name. We'll just call it SCT, single cell transformation. We'll go ahead and run this. This does take a fairly long time on Windows. I don't know if Mac or Linux has the option for transformation to parallelize it. But as far as Windows goes, unfortunately, I have not been able to figure out how to do the transformation, PCA, or UMAP parallel. The find neighbors and find clusters is actually fairly quick, which is nice. But some of these other things with 188,000 cells that we can see, it does take a really long time. So I'll let this run, and then I'll come back when this is finished. There we go. You can see there that somewhere along the way, the memory got awfully high. It's like 44 gigabytes. Let's go ahead and see if our garbage collection will clean anything up here. There we go. We're back down to 11. So 1392, somewhere in there. Okay, now we have transformed data. Let's look at our object here and see if we refresh this. Our assays, we have 4. Awesome. SC, it should be the same size as our RNA, and it looks like it. Fantastic. And there we go. And we have our scaled data, which is actually in here. Cool. All right. So let's go back here. So now that we have our scaled data, we can actually run a PCA. So let's just do PCA. Again, we'll have our output as our object. And something to note, if you have a lot of memory, then you can do like object 1, object 2, just in case you want to go back and rerun something and don't have to rerun something, change the name, then you don't have to worry about deleting it. It's easy enough. So if you want to rerun SCTransform and have the output be SCT still, what you can do is just rerun it. If you want to change the name to something different than SCT, you should be able to remove this the same way that we removed the other one. Just assign it as null in this guy, just like this. It's up to you. It just, like I had said, it takes a lot of memory. The transformation there got up to 44 for the total R environment. I would recommend 64 for this particular assay, depending on how many genes that you have. If you have 1,000 genes, of course, you're not going to need that much. But as technology gets better and better, more and more genes are going to be included, and a cluster is something that would be very nice to have. If we want to run a PCA, the function is just running PCA. The object will pass in our object, the assay, so just like our SCTransform, we want to tell it to now use SCT. So we want to run a PCA on our normalized data. The output, so let's go ahead and do this. That way it doesn't seem like I'm talking crazy. The output will actually call capital P, capital C, capital A, but we name that by reduction name, reduction.name, PCA, all capital. And then we can tell it how many dimensions that we actually want to calculate. For the UMAP, we'll use 30, which seems to be the default. For work, I used 50, but the UMAP is calculated from PCA, right? So if we start at 30 and later on want to jump to 50, we would have to rerun our PCA if we keep only 30 for our PCA. So here, NPCs, I'm going to set at 50. So let's go ahead and run that. This, like I had mentioned before, is also going to take a little bit, not nearly as long as the transformation, if I remember correctly, but it does take some time. So when that's done, I will come back. All right, it looks like our PCA has finished. And we can see here from the number of dimensions to print, prints out the first 5, and it prints genes that are associated with them. So later on, we might be able to come back and see that something that we have is associated in one way or another with our data, which is pretty cool. Now, with the PCA calculated, we can go ahead and view this in a dimension plot, and we can look at the first and the second principal component. And to do that, let's view PCA. It's actually called a dim plot. And something that I've noticed with this version of R, unfortunately, 4.1.2, just like with my work one, leaving it on default when printing, unfortunately, does not yield any points. So this is something that I might have to put in an issue into GitHub for Seurat, which is really unfortunate. But we can use object. What we want to look at, well, we want to look at the reduction of our PCA. So this here has to equal our reduction here. And then, so let's go ahead and look at this. We kind of see what I mean. So raster as false, which means that it'll plot all of the points, is the only way that we're able to see the points, unfortunately. So if we leave it as default, it converts it into an image, and none of the points are actually saved. So if we want to look at our plot, we need to put in raster equals false. And this takes much longer because it's actually rendering all of the points here. So when it's done, it'll pop up. There we go. So now we can see our principal components. Doesn't really look like much, so take that with a grain of salt. But we're able to look at our PCA. Moral of the story. But in order to get anything that really stands out, we want to look at our UMAP. So we'll do, we'll run UMAP. And just like with running PCA, we can do run UMAP. Woohoo. Object. What do we want to run it on? So we'll set our reduction, just like with the PCA. PCA. So the UMAP uses our PCA first. Reduction. Okay. What do we want to call this? Well, we have to do a reduction name, and we'll call it UMAP. Perfect. Dims, we'll do 1 to 30. As I said, it seems pretty typical. And then a lot of times we'll see UMAPs and they look just perfect. Let's see, this guy, like they look perfect. That's not usually default unless you have very different cell types. So what I will do is something that I've kind of learned along the way. It's using a repulsion. So it's going to take like the center of mass of a particular group and push it away. So repulsion, you'll kind of see what I mean from this. Repulsion strength. And if we do the same thing for this, copy question mark paste. Repulsion strength here. It's defaulted to 1, but in order to get the clusters that really kind of stand out from others, we'll set this to 10. And it'll look much better. So we'll go ahead and run this. I don't think it'll take too awfully long, but when it's finished, then I'll come back and we can do another dim plot for our well, let's actually throw that in here. So we'll copy it, we'll paste it. What we want to do is we want to view our UMAP. So we have our object, reduction, UMAP, and again, we have to have our raster equals false. So now I will come back when this is finished. All right, it looks like our UMAP has now completed. So let's go ahead and run our dimension plot with raster as false. And you'll be able to kind of see the clusters pushed away from each other, as opposed to kind of connecting. There you go. So we have a pretty distinct cluster down here, 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 over here, so on and so forth. But they're all the same color. So the next step would be something like identifying the different clusters with the PCA data. And we'll use the same 30 PCAs that we had used for the UMAP. That way clusters overlaid on top of this will make sense in this two-dimensional representation. So we'll do object. Let's finding clusters. Great. So we'll call this one our object again, equals find neighbors. There we go. We want to pass in our object. The reduction that we want to use is our PCA. And then the dimensions, we want to keep it the same as what we used for our UMAP. So we'll do 1 to 30 again. So we'll go ahead and run that. While that's running, we can queue up the next code. So object equals find clusters. Let's see if it'll pull. Nope. Find clusters. We'll pass in our object, the algorithm. We'll set as 1. This is just the low vein clustering, which is very common. A resolution, oh shoot, I don't remember how this goes. I think the higher the resolution, the more clusters that are identified, and the lower the resolution, the less clusters that are identified. So this is something that if you're going to do this assay or use this technology for your experiments, you'll want to play around with this resolution parameter, as well as probably some of the dimensions, just to make sure that what you see really stands out. The repulsion strength can also be upped if you want some super tight clusters there. But let's go ahead and run this find clusters now. So you can see that with our algorithm 1, we're using low vein. I'm hoping that this goes rather quick, but I'll come back when this is finished, and then we'll look at the final. We can queue this up. So let's look at clusters on UMAP. And to do that, we'll go back to our trusty dim plot. We'll pass in our object. The reduction that we want to see is going to be our UMAP, because remember we had our 30 dimensions of our PCA to build our UMAP, and we have the 30 dimensions of our PCA to build our neighbor map. Let's go back down here. And then we can do group by, and there's going to be a column, and we'll have to check what column that is when it's all finished. And then again, we'll have to set raster as false. So then we get all 188,000 points being plotted. So when that's done, we'll come back. All right, it looks like our clustering has been finished. So let's go ahead and look at what that new column was that it had created. So let's do call names of our object, and then in our metadata, there we go. Okay, so we use a resolution of 0.3, so we'll be able to use the SCT SNN res 03. So we'll go ahead and paste that in there. And let's look at what the new clusters look like on top of our UMAP. It takes so long since we are not able to use the raster equals true. There we go. So we can see this is just a two-dimensional representation that use 30 dimensions though. So there are some points that fall outside, but we can see that we have this cluster 0, cluster 1, looks like 13 maybe over here, 11, 12, so on and so forth. So it looks like our clustering had picked up our different, clusters of cells with our PCA. So that's great. So now next time what we'll be able to do is we'll pass this into in situ type, hopefully, if we're able to get it to work. And then along with a single cell reference, and with that we should be able to identify which cell type these clusters are. So I know this is really long, but I really appreciate you watching. If you have suggestions for other videos or you do find this interesting, leave a comment. Go ahead, and then I will see you next time.